Hello. This study is entitled The Synthesis of Short-Chain Vinylimidazolium-based Dicarboxylate Ionic Liquids as Supercapacitor Electrolytes. Now, it's quite a mouthful, so let's break it down, starting with the supercapacitor. I think the best way to illustrate what a supercapacitor is to compare it to more traditional energy storage devices. Let's start with the difference between the battery and the capacitor. The key difference between the two is that batteries store energy in the form of electrochemical energy, whereas capacitors store energy in the form of electrostatic charge. Because capacitors don't rely on chemical reactions to charge and discharge, they are less susceptible to corrosion, meaning they have a longer lifespan compared to batteries. Capacitors are also more reliable and cost-effective. They have a higher power density, meaning they charge faster than batteries. Despite their advantages, however, they have one major drawback. They can't store as much energy as batteries. Bridging the gap between batteries and capacitors is the supercapacitor. They have a higher capacitance, so they are able to collect and store more energy than regular capacitors, meaning they have a higher energy density. They are also able to charge and discharge quickly, like capacitors, and therefore have a higher power density compared to batteries. Supercapacitors also address several disadvantages of typical energy storage devices, such as self-discharging, low life cycles, and negative environmental impact. So why haven't they taken over as alternatives to batteries? Despite being an improvement over the energy density of traditional capacitors, supercapacitors still can't compete with batteries when it comes to energy density. Current supercapacitors on the market would have to be 2 to 3 times thicker in order to be able to compete with the energy density of the batteries, making them impractical for most applications like in electronic devices or motorized vehicles. So, how do we attempt to solve this problem? Well, a lot of research is going into changing different components of the supercapacitor, and in this study, we are changing the electrolyte. We want something that is both conductive and has a large electrochemical stability window. Most electrolytes available in the market are either organic or aqueous, and both have their disadvantages. Aqueous electrolytes have a narrow electrochemical window because of water. Organic electrolytes, on the other hand, are highly volatile and can be harmful to the environment. In this study, we synthesized vinylimidazolium-based ionic liquids as supercapacitor electrolytes. Now you may ask, what are ionic liquids? Well, they are salts that exist in liquid form at room temperature. They are non-flammable, non-volatile, stable, conductive, and are known to have a wide electrochemical stability window, meaning there is a large potential window where they don't reduce or oxidize, which is an important factor when it comes to improving the energy density of supercapacitors. Vinylimidazolium was chosen as the cation because it can be explored in future studies as solid electrolytes, and dicarboxylates were chosen as the anions because previous studies have shown they can improve ionic conductivity and electrochemical stability window. The objectives of this study are to synthesize the vinylimidazolium-based dicarboxylate ionic liquids, to confirm their structures via proton NMR, carbon NMR, and FTIR spectroscopy, and to evaluate their electrochemical properties via ionic conductivity tests and cyclic voltammetry. The methodology can be simplified into 2 parts. First is the synthesis of the ionic liquids, and second is the electrochemical characterization of the ionic liquids. For the synthesis of the ionic liquids, a precursor halide was first prepared through solvent-free sonochemical synthesis of 1-bromobutane and 1-vinylimidazole. The precursor halide was then exchanged through an anion exchange column to obtain the dicarboxylate IL. The structures of the final products were confirmed using FTIR, proton NMR, and carbon NMR spectroscopy. The electrochemical characterization was done through ionic conductivity measurements using an ionic conductivity meter, and cyclic voltammetry was used to determine the electrochemical stability window. The dicarboxylate ionic liquids were synthesized from the precursor halide ionic liquid, and the products were noticeably lighter in color. They were slightly less viscous than the precursor IL, and it was observed that increasing the alkyl chain length of the dicarboxylate increases the viscosity of the ionic liquids. The appearance of a chemical shift at around 165 parts per million in the carbon NMR spectra of the dicarboxylate IL signifies the presence of a carboxylate group from the dicarboxylates, indicating that the dicarboxylate IL was successfully synthesized. For the ionic conductivity tests, it was observed that the longer or larger the dicarboxylate was, the lower the ionic conductivity. This was expected because longer dicarboxylate chains increase van der Waals interactions, leading to higher viscosity and therefore lower ionic motility. The oxalate ionic liquid had the highest conductivity, owing to oxalate's relatively smaller size compared to the other dicarboxylates. As for the results of the cyclic voltammetry, there was no clear trend on the width of the electrochemical stability window with respect to the length of the dicarboxylate anion, but they were all around 4 volts, which is 4 times that of the electrochemical stability of aqueous electrolytes and around 1.5 times that of organic electrolytes. To wrap it all up, dicarboxylate ILs were successfully synthesized as confirmed by the FTIR, proton NMR, and carbon NMR spectroscopy, and all synthesized dicarboxylate ILs exhibited outstanding ionic conductivities and electrochemical windows at more than 360 microsiemens per centimeter and about 4 volts, respectively, making them promising candidates for supercapacitor electrolytes. I would like to acknowledge the work of Lester Dave G. Pua, Jonathan N. Patricio, Dr. Susan D. Arco, without whom this work would not have been completed, the Synthetic Organic Chemistry Laboratory, where this study was performed, and this study was funded by DOST Pasherd and the Natural Sciences Research Institute. Thank you for listening.